Welcome to General Chemistry. This is Jim Burnham. Today we're talking about chemical quantities. What is the SI, the metric unit for measuring the amount of a substance? You may recall it is the mole. These are the 7 base SI units. Time is seconds, length is meter, mass kilogram, electric current is ampere, temperature Kelvin, luminous intensity candela, and the amount of something is the mole. So we've got to get comfortable with the mole. Now in this section we're going to be looking at molar mass and molar volume. In the first section we learned 3 new terms to represent the moles of different substances. Gram atomic mass, so that's the mass of a mole of atoms. Gram molecular mass, the mass of a mole of molecules. And gram formula mass, the mass of a mole of formula units. But we can use one term to cover all those other terms, molar mass. So that's the term we're going to use, molar mass. Rather than using those other 3, gram atomic mass, gram molecular mass, gram formula mass, we're just going to use the mass of a mole of whatever we're talking about. So molar mass is the mass in grams of 1 mole of whatever substance we happen to be talking about, whether it's atoms or molecules or formula units. All right, here's a sample problem. How many grams are in 9.65 moles of dinitrogen trioxide? All right, so the first thing we list our knowns and our unknowns. We have the number of moles. We can figure out the molar mass just based on the atoms that make up that molecule, and now we're looking for the mass. So here's our setup. We start with 9.45 moles, right? Our conversion factor is going to be grams, right? We're trying to get to grams in our answer, so it's going to be grams per mole. So 76 grams in 203 per mole, and these cancel out our moles, leaving us with grams of N2O3, 718. Does this make sense? Sure. If 1 mole has a mass of about 76, then 10 would be somewhere in the 700s. And our answer is in the 700s, so that makes sense. And we rounded it to the proper number of sig figs 3. All right, another sample problem. Find a number of moles in this many grams of iron 3 oxide. So here we're starting with a mass and we're converting to moles. In the previous problem we started with moles and we converted to mass. So we start down here with our 92.2 grams of iron oxide, iron 3 oxide. We convert that now to moles per gram because we're going to cancel out our grams, right, and convert it to the units that we want, moles. So we use this conversion factor. Remember, conversion factors can be flipped any way we need them because they're equalities. In this case, we're going to put grams on the bottom to cancel grams here, so we end up with our answer in moles. And when we take the molar mass, 159.6 grams, again, we just use the periodic table to find that. We do the calculations, we get 0.578 moles of Fe2O3. And that's the right number of sig figs. Does this make sense? Yeah. Since what we're starting with is slightly larger than half the molar mass, the answer should be slightly bigger than half a mole, which is what we're seeing. Okay, so remember, molar mass equals the atomic mass expressed in grams. Remember, that's what molar mass does. It takes the atomic mass from the periodic table and converts it to grams. So the atomic mass of carbon is 12.01 in atomic mass units. Well, to get that in grams, we need an Avogadro's number. That's what molar mass is. It's atomic mass expressed in gram weight. Now, if there's a chance of confusion, for example, someone says, hey, what's a mole of oxygen? How much is a mole of oxygen, right? That could mean oxygen as a diatomic molecule, right? O2, or it could just mean a single atom of oxygen. And so in that case, we would say, hey, do you mean gram molecular oxygen or gram atomic oxygen? And so they would have to tell us that. Or it could even mean, ozone, because that comes as a triatomic molecule. So if we need one, we'll use a more specific term, but otherwise we'll use molar mass in place of the mass of an atom, or the mass of a molecule, or the molar mass of a formula unit. Now with liquids and solids, the volume of a mole can vary tremendously. Here are moles of different substances. Here's a mole of sulfur. Here's a mole of mercury oxide. Here's a mole of copper. See, it's quite a bit smaller because the atoms are small. So an Avogadro's number of copper takes up less space than Avogadro's number of, say, sugar, these are bigger molecules, so they take up more space. Here's an Avogadro's number of copper sulfate, an Avogadro's number of table salts. But this varying of volumes doesn't happen with gases. This might be somewhat unexpected, and we will look at this in a later chapter when we tackle the gas laws. But for now, the volume of any gas is about 22 liters at standard temperature and pressure. So just imagine 11 2-liter bottles of, say, soda. All right, so here's close to 11 bottles, 12 bottles, I think. That is how much volume any gas, every gas, takes up at standard temperature and pressure. And what that means, standard temperature and pressure, is 0 degrees Kelvin and 1 atmosphere. That's what standard temperature and pressure is always going to refer to. And so the volume of 1 mole of any gas at that standard temperature and pressure is going to be 22.4 liters. That is molar volume. You want to commit that number to memory. The molar volume of any gas at standard temperature and pressure is 22.4 liters per mole. This quantity is the molar volume. Commit it to memory. They may have different weights. Gases may have different weights, but they will always have the same volume. So even though a mole of nitrogen weighs 28 grams, right? It's a diatomic molecule, N2, should be a 2 right here. And a mole of hydrogen weighs 2 grams. They will both take up the same space, namely 22.4 liters at standard temperature and pressure. So it doesn't matter what the gas weighs, it will still take up the same volume. Determine the volume of 0.6 moles of SO2 gas at standard temperature and pressure. So we're simply going to convert from moles of gas to liters using this molar volume ratio. So 0.6 moles of SO2, and we know that for every mole of SO2, put it down here because we want to cancel these units, that will give us liters of SO2. There's 22.4 liters for every mole, and this will cancel out moles and give us liters, and we end up with 13 liters. Does this make sense? Well, sure. 1 full mole would equal 22.4 liters. This is a little over half, so our answer should be a little over half of 22.4, or around 13. Sure. And it should have 2 sig figs because that's all that we have here in this number. The 2 digits here limit how many sig figs we can use in our answer. All right, another problem. The density of a gaseous compound containing carbon and oxygen is so many grams, 1.964 grams per liter at standard temperature and pressure. If you ever see this standard temperature and pressure, you should think to yourself, hey, molar volume, 22.4 liters. Determine the molar mass. Now remember, density is grams per liter, and we're trying to go to molar mass, which is grams per mole. Right? So we need to convert from liters to moles, or in this case, grams per liter to grams per mole. So we just start with what we have. We start with our grams per liter, and then we're going to use our conversion factor, 22.4 liters. In this case, we're canceling out from the denominator to the numerator, right? And we're going to end up with grams per mole, which is what we want. So here our liters cancel, and we're going to end up with grams per mole, which is our desired units. We crunch the numbers, and we can't use all these digits here. We have 4 sig figs here, 3 sig figs here, so we can only keep 3 sig figs in our answer. That will round to 44.0 grams per mole. The mole roadmap. All paths lead to and from the mole. I call this the mole roadmap or molar island, mole island. Basically, with the mole, we can convert from mass to mole using the molar mass, and then from mole to number of particles by multiplying that by the Avogadro's number that we have. So if I have 1 mole of something, I multiply it by Avogadro's number to tell me how many representative particles I have. Or if I have a super high number, I divide it by the number of Avogadro's particles to tell me the number of moles. And now I can also use moles to convert to and from molar volume, the volume of a gas at standard temperature and pressure. So notice how versatile this mole is. It allows us to go from weight to volume, or weight to number of particles, or any of these other conversions. So it allows us to convert from volume to mass, volume to particles, particles to mass, or particles to volume. So we can do any one of these relationships by going to and from the mole. Remember in the previous section we measured apples in 3 different ways. We measured them by count, by weight, and by volume. Well, and we related all 3 of those to the common term dozen. Well, now we can convert between volume, mass, and particle number using the relationship to a mole. Think of the mole as the chemist's dozen, right? The central term that connects all the other terms, except instead of dozen, we're using a much, much bigger number, an Avogadro's number. All right, so just, again, this is another way to represent how we can go from weight, okay, through molar mass to mole, from mole to number of particles and back, and from mole to volume of gas and back. And so we can go from particles. So let's say I have 6.02 times 10 to the 23rd particles of carbon dioxide gas. How much volume would that be? Well, that would be 1 mole, and every mole has 22.4 liters. Therefore, I would have 22.4 liters of carbon dioxide gas. If I had that a mole of carbon dioxide gas, what would it weigh? Well, we would just multiply that times its molar mass, and we would get, what is it? It's 12 and 32, 44, so it would be 44 grams. So I can go from particles to mole to volume, back to mole to mass. And now the math. It's finally here. Let's start with percent composition. So we can calculate percent composition, and from that we can calculate chemical formulas. All right, let's start with the first. How do we calculate the percent composition of a compound? Well, what do we mean by percent composition? The part, how much is the part related to the whole? Here, this is a quarter, right, of the pizza. This is 25% of the whole pizza. That's all percent composition means. How much of the part do we have of the whole thing? So if I cut a watermelon into 2 halves, right, each half is 50%. If I cut it into quarters, right, each quarter is 25%. So in this case, I would have 3, right, out of a total of 8. So 3 out of 8 parts would be my percent composition of this to the whole. So again, it's just a simple math problem. Percent composition is part in the numerator over whole in the denominator. What percent of 94 is 42? So 42 is what part of 92? Well, we say 42, the part out of the whole, 92 times 100 gives us 45.7%. Right. Well, in the case of elements and compounds, we're looking for the relative amount of an element, that's the part, in the whole compound. And we're looking at percent by mass, percent by weight of each element in the whole compound. So if we're looking, if the question asks us to find the percent mass of an element, okay, we're going to take the molar mass of the element, that's the part, over the molar mass of the whole compound, and then multiply that by 100%. So here's a great sample problem for this. All right, so they want us to find the percent composition of a compound. So we have an 8.2 gram piece of magnesium, and it combines completely with 5.4 grams of oxygen to form a compound. So this is one part of the compound, the magnesium part, and this is the oxygen part, and then together there's going to be a whole new compound. Well, we know what the mass of the compound is. right? The mass of the compound is going to be the sum total of the parts. Remember, whatever we start with has to be in the product. So if our reactants are an 8.2 gram piece of magnesium and a 5.4 gram of oxygen, then the mass of the compound formed because of conservation of mass, the product is going to weigh 13.6 grams. So we just need to find out what percent magnesium is of the whole and what percent oxygen is of the whole. So we're just going to take our mass, our given mass of magnesium over the mass of the whole. So our mass of magnesium is 8.2 grams over the mass of the whole compound, 13.6, times 100% is 60.3%. We do the same thing with oxygen. We take the mass of oxygen, 5.4 grams, over the grams of the whole compound, which is 13.6, just like it was here. And we just do the math. 5.4 divided by 13.6 times 100, 39.7%. Check, does it make sense? Well, it will if these two add up to 100%, which they do. Okay, so here's how you do any percent composition problem. All right, so let's say we wanted the percent composition of propane. So since it's made up of two different elements, we would find the total amount of carbon out of the whole and the total amount of hydrogen out of the whole. So we list the elements, we count the atoms, we multiply the atoms of each element, in this case 3 carbon, by the atomic mass of the element. We would do the same thing with the carbon, with the hydrogen. There's 8. And then we express each element as a percentage of the total molar mass. To calculate the percent carbon, we turn each one of these, so we have 3 carbon atoms. Say, listen, let's just have 3 moles of this. Okay, 3 moles of that is going to be 36 grams. That's 3 times 12. Okay, out of the total weight of this, what would the total weight of this be? Well, it would be the 3 carbons, 36 grams, plus 8 hydrogens, 1 gram. So the total of the whole compound would be 44. So the carbon percent is 36, that's the molar mass of the carbon, over the molar mass of the whole thing. 36 grams out of 44 times 100, 81.8% propane. The remainder, of course, now we could just subtract this from 100 to get the remainder, but let's do the work. For the percent hydrogen, we're going to have 8 hydrogens, so the molar mass of 8 hydrogens is 8. And again, the molar mass of the whole total is what we calculated here before, 44. 8 divided by 44 times 100 is 18%. Does this make sense? Yeah. Together, this makes up essentially 100%. All right, let's practice. Let's calculate the percent composition of magnesium carbonate. So here's our formula. We have a magnesium, a carbon, and 3 oxygens that make up this formula unit. And now, so we want to find out what's the mass of the whole thing. Well, let's just find out the parts, the molar mass of each of the parts, right? So the molar mass of magnesium is 24.3. The molar mass of the carbon is 12, and then we have 3 oxygens at 16 grams each. So the mass of the whole compound, the molar mass of magnesium carbonate is 84.34. We're going to use that in each one of these as the whole, right? Because percent composition is the part of the whole, part of the whole, part of the whole. So the magnesium part is the molar mass of the 1 magnesium over the whole that we just calculated times 100. So it's 28.8% magnesium. Okay, 12 over 84, 14.2% carbon, 48 for the oxygen out of 84 is 56.9%. Those add up to 100%. So this is 28% magnesium, 14% carbon, and 57% oxygen. We've already done this problem, but you can just see we just take the molar mass of the carbon over the molar mass of the whole, and the molar mass of the hydrogen over the molar mass of the whole, and gives us those percentages. Now we can use percent as a conversion factor. So we can use percent composition to calculate the number of grams of an element in a given amount of a compound. So remember, back in the propane problem that we've done twice now, we found that the propane was 81.8% of the whole compound. It was 81.8% carbon. Now remember, percent means amount out of 100. So 81.2% carbon means if we had 100 grams of something and it was 81.2% carbon, 81.2 grams of that 100 grams would be carbon. So basically, you convert percentage to grams, assuming that you have a 100-gram sample. Right? So that's our ratio, right? 81.2 grams per 100 grams of propane. And this will give us the mass of carbon in any given amount. So let's say we start with 82 grams of propane. How much is carbon? Well, start with 82 grams of carbon, use our conversion factor, 81.8 grams per 100 grams of propane. So our grams of propane cancel. We're left with grams of carbon, namely 67.1 grams of carbon. So we have an 82 gram sample of propane that's 80% carbon, therefore 67.1 grams of that end up being carbon. Does this make sense? Yeah. If you said 80% of 80, it would be 60 something, right? And that's what we have, 67. Okay, we can also use percent composition to calculate empirical formulas. All right, what on earth is an empirical formula? Well, it's the lowest whole number ratio of the elements of a compound. Remember, empirical formula, lowest whole number ratio of the elements. So, for example, a compound might have an empirical formula. So if we know if a compound is built out of carbon and oxygen, we're gonna find the ratio, lowest whole number ratio of carbon to oxygen. And the lowest here might just be 1 to 1, 1 carbon to 1 oxygen. The empirical formula, this is important, may or may not be the same as the actual molecular formula. The molecular formula as the molecule really and truly exists. So here's an example of the difference. If we calculated the empirical formula for hydrogen peroxide, we would find that the hydrogen and the oxygen are in a 1-to-1 ratio. So we would just say the empirical formula is HO, 1H, 1O. However, we know that the molecular formula for peroxide is actually H2O2. So you can see that the molecular formula is always going to be a whole number multiple of the empirical formula. And the empirical formula may or may not give you the actual molecular formula. We'll have to have more information. So remember, the empirical formula is just the lowest whole number ratio of moles of atoms. And the lowest whole number ratio of this, even though they come 2 and 2, is you can cancel these out, and the lowest ratio is 1 to 1. So that would be the empirical formula, but this would be the actual molecular formula. Okay. So how do we determine the empirical formula? Well, we're going to start by calculating using 100 grams of a compound. And we're going to determine the moles of each element in 100 grams of compound. So we're going to start with percent composition. Remember, then we're going to turn that from a percentage of the whole into grams of the whole. Then we're going to determine the moles in that many grams. And then we're going to do some more work here. We'll see. So here would be a sample problem. So we analyze a compound, and it's found to be 25.9% nitrogen and 74.1% oxygen. And now it's asking us, what is the empirical formula for the compound? Okay, so the first step, step 1, let's turn these percentages into grams. All right, so if it's 25.9% nitrogen, then 25.9 grams of nitrogen would be available in a 100-gram sample. So let's just say, okay, let's start with 25.9 grams. So we convert percent to grams, and we're going to start with 74.1 grams in our 100-gram sample. That's oxygen. Okay. So step 1, assume a 100-gram sample. Our percentages turn to grams. Then we're going to go from grams to moles by multiplying by our molar mass. Okay, so we're going to say, hey, I can convert from grams. I have each mole of this has 14 grams. My grams will cancel. Now I've got moles. I've got 1.5 moles of N. Okay, I'm going to do the same thing with oxygen. Okay, take its grams, multiply it by its molar mass, and cancel out grams to moles. So now we have, in blue, 1.85 moles of N and 4.63 moles of O. So that's step 2, right? We've converted grams to moles. Now, step 3, here's the magic. We divide all of our molar quantities by the lowest number of moles. So which is lower, 1.85 or 4.63? Well, 1.85 is the lowest molar quantity. So we're going to divide both of these blue things by the lowest number. So this 1.85 is going to be divided by itself, 1.85. And this 4.63 is going to be divided by the lowest molar quantity, 1.85. And what we're going to see is that, obviously, this divided by this is going to give us 1. This divided by this is going to give us 2.5. Now, that's not a whole number. So we're going to just start multiplying both of these red numbers until we get whole numbers for both. And as you can see, to turn 2.5 into a whole number, I have to multiply it by 2. But whatever I do to 1, I have to do to both. So I'm going to multiply both this red 1 and this red 2.5 by 2 to turn it into 2 and 5. Now we have a whole number ratio. This means I have 2 nitrogens to every 5 oxygens. And that is my empirical formula. N2, O subscript 5. The 2 is this 2 right here. This 5 is this subscript here. I have now calculated the empirical formula starting with a percentage of a compound. And from that, I can then calculate molecular formulas. Okay, remember, the empirical formula is simply the simplest whole number ratio of elements. Right? The molecular formula, the actual ratio, is going to be some multiple. It might be the empirical. So here, CO2, 1 carbon to 2 oxygen, that actually turns out to be the actual molecular formula. So these are the exact same. Okay? In water, we calculate 2 hydrogens for every oxygen. Well, that turns out to be the actual molecular formula as well. Okay? In another compound, we might find it's 1 nitrogen to 2 oxygen, but the actual molecule is going to be double that. It's N2O4. Here's the lowest whole number ratio. Here's the actual molecule. Notice this is a multiple of this. This is 2 of those. Okay? Likewise, here's the empirical formula, 5 to 11. Actual formula, 10 to 22. Again, it's double this. Here's the lowest whole number. Okay, 2 to 6 to 1. The actual is a triple. It's 3 times that. C6H18O4. Notice it's either going to, the molecular formula is either going to be the empirical formula or it's going to be a whole number multiple of the empirical formula. So some other examples where this is 6 times the empirical formula, this is 2 times the empirical formula, 6 times the empirical formula. It's the same as the empirical formula. Okay, so how can we convert from empirical formula to some multiple, or in that multiple it might be 1, to get molecular formula? Well, we need one more piece of information. We need to know the molar mass of the whole compound, the actual compound. And that molar mass will either be the same as the empirical mass, in which case then the empirical formula and the molecular formula are identical, or the molar mass will be a whole number multiple. And depending on what multiple it is, if the molar mass is twice as heavy as the empirical mass, then the molecular formula will be the empirical formula doubled. If it's triple, we're going to triple the empirical formula, and so on. So we're simply going to divide the bigger one, if it is bigger, and if it is bigger, that's the molecular mass, by the smaller one, the empirical mass. And this gives the number of empirical formula units in the molecular formula, in a whole molecule of the compound. So we just multiply the empirical formula by this number to get the molecular formula. So here's what we have. We have the molar mass of the empirical formula. So here's our empirical formula, which we may have determined, for example, by a percent composition problem. C6H7N. Okay, and we just figure, okay, what's the molar mass of this? Okay, well, we've got 6 carbons at 12 each, and 7 hydrogens at 1 gram each, and 1 nitrogen at 14 grams, so a total of 93 grams for the whole thing. Now, what is the actual mass of the actual molar mass of the molecule that we have? Well, this one turns out to be 186. This is the extra piece of information they have to give you. So if the actual mass is 186.28, we just divide this big one by this little one that we calculated. It turns out to be 2. Great. That means we're going to double the empirical formula. Whatever this number is how many multiples of the empirical formula we need to give us the actual molecular formula. So we're going to take the entire empirical formula, multiply it by 2. That's the ratio we got. And that turns everything, we just double everything. C6 becomes C12, H7 becomes H14, N becomes N2. All right, key concepts, mole island. Mole island is this is the central concept in chemistry for converting from weight to number to volume and back again. So again, if you start at particle island, and if you want to go from particles to mole, then you either multiply or divide, depending which way you're going, to get to a mole. Then if you want to go to volume, you either multiply or divide by 22.4. Or if you want to go to grams, then you either multiply or divide by molar mass. All things go through the mole. So if we have moles and we multiply by molar mass, so 1 mole of carbon times its molar mass of 12 gives us 12 grams of carbon. 3 moles of oxygen atoms times their molar mass of 16, right, would give us 48 grams of oxygen atoms. If we take mass, so we have 36 grams of carbon, and we divide it by the molar mass, 12 grams per mole, then we can tell we have 3 moles, right? If we take the mass, 36 grams, we divide it by the grams per mole, we get 3 moles of carbon if we have 36 grams. Again, the mole allows us to count by weighing. A mole of any gas at standard temperature and pressure, that's 1 atmosphere and 0 degrees Celsius, is 22.4 liters, no matter what the weight of the gas is. The volume will be the same. Now the density will change because the density is going to be the molar mass divided by the volume. Right? So in this case, the density will change because molar mass of a heavier gas will be higher, and therefore the density, the weight per volume will be higher. But all gases of whatever weight at standard temperature and pressure take up the same volume for a mole, 22.4 liters. Percent composition is the percent mass of each element in the whole compound. So it's the percent that the part weighs of the whole compound. And empirical formula is the lowest whole number ratio of atoms in a compound. It may or may not be the same as the molecular compound, but the molecular compound is always going to be a whole number multiple of the empirical formula. That's it. Thanks for your time.